Good morning or good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is Stefan from Business Review, and I will be your host. It is our pleasure to have Eva's Capacitor company with us today, who will be presenting this webinar titled Hybrid Capacitors for Hi-Rel Applications. Today's guest speaker is Misha Pierre-Mike, Sales and Marketing Manager. Before we begin, I'd like to welcome you to the webinar platform On24. You'll notice that the webinar is browser-based. If you happen to disconnect for any reason, please just click on the link you received via email to rejoin the session. To ask questions, you can do so via the Q&A widget on the top right-hand side of your screens. Just type your question into the box and click Submit. We'll allocate some time at the end of the session to address any questions or thoughts that you may have. Please use the yellow Help widget if you require any assistance, and please keep in mind you can move, resize, and maximize any of the windows in front of you for a better view of the slides. But now, please allow me to welcome Misha.
Thank you for that introduction, and thank you to everyone for taking some time out of your busy schedules to participate on this webinar. The process of buying capacitors has changed a lot in the last several years. Today, there are a wide variety of capacitor options to consider. Choosing the right capacitor for your specific application will play a huge role in determining the performance, reliability, and size of your system. So during this webinar, we'll start off by reviewing some capacitor basics. Then we'll compare some of the different capacitor technologies available today. We'll go through a list of critical points to think about when choosing a capacitor for a Hi-Rel application. Then we'll apply this logic as we step through some real-life case studies of practical applications, where we'll calculate our capacitance needs and evaluate several potential solutions. Finally, we'll review how ESR impacts capacitor performance and conclude with how Evans caps work, their unique characteristics, and how they compare to other capacitor options. So what is a capacitor? Simply put, a capacitor is a passive device that stores electrons. Capacitors operate much like batteries in the sense that they both store electric energy. However, capacitors can release their stored energy much faster than a battery. Capacitance is a measure of the storage potential of a capacitor. Although capacitors come in a variety of different shapes, sizes, and technologies, they all perform the same basic task. Now, let's take a moment to review three of the major capacitor categories. Electrostatic capacitors consist of a dielectric sandwiched between two plates. Electrostatic capacitors can operate at high frequencies and voltages and are more practical for AC applications. An electrolytic capacitor contains an electrolyte that takes advantage of high surface area. The high surface area lets electrolytics provide high capacitance values and are typically used in DC applications. The term supercapacitor is somewhat of a marketing term, but it is understood to mean carbon-based, or EDLC, electrochemical double-layer capacitors, and takes advantage of extremely high surface area to provide very high capacitance values, typically at lower voltages and frequencies. While these are the major families of capacitors, there are many others, especially when it comes to niche applications and technologies. Now, we'll discuss where capacitors are used and the area we'll focus on today. Capacitors are found everywhere, from consumer electronics to complex military and aerospace systems. It is estimated that over 1 trillion capacitors are sold annually. The focus of today's webinar, and Evan's focus, will be on low to medium voltage applications, typically defined as 10 to 125 volts, operating at less than 10 kilohertz, where swap or space, weight, and power savings are critical design considerations. Applications requiring capacitors that fall within these operating parameters typically include radar transmit pulses, high power pulse laser, electronic warfare, and power holdup in avionics. I'm going to spend a few minutes stepping through some key parameters that must be considered when choosing a Hi-Rel capacitor for Hi-Rel applications. In comparing all options, we must be mindful of how the capacitor performs, especially under varying conditions. Some applications expose capacitors to extreme environments, such as high shock and vibration, low or high temperature, radiation, and moisture. Capacitors not only must survive these various environments, but also need to minimize performance variation as these environments change. Reliability is the defining point of a Hi-Rel application. Designers want capacitors with a proven record of success and are designed to adhere to critical military specifications and space-level screening requirements. Understanding the capacitor's shelf life limitations, how they are derated, if they outgas, and how they fail at end of life will impact how well suited they are for operation within a specific system. Swap savings requirements are becoming the norm. Finding a capacitor that meets specific size and weight requirements, in addition to providing robust and reliable mounting options, is key to designing within mechanical constraints. Some capacitor technologies can even swell over time, so designing in enough space around the capacitor to account for this must be considered. A capacitor's electrical performance will contribute to overall system efficiency. Capacitors with high ESR can generate more heat and contribute to voltage droop. Understanding current handling limitations, cycle limits will have a large impact on how the system is designed. As we discussed, capacitors are used everywhere, but in today's webinar, we're going to narrow our focus to some common Hi-Rel, low to medium voltage applications that include power holdup, typically designed per mil standard 704 or DO 160 avionics standards, radar, and laser. Regardless of our application, capacitors must supply a certain amount of energy for a specific period of time. On this slide, we see how different applications vary. For example, power holdup applications require capacitors to provide lower levels of power, but for longer periods of time. Whereas in radar applications, more current is needed for an even shorter period of time. Laser applications take it one step further, requiring even more power, but for less time. The formula to calculate our capacitance needed for all three of these applications is the same. We multiply our current by our pulse width and divide it by our allowable voltage droop. Now let's step through some specific case studies. In this example, we have a power holdup application where the current is 1 amp, the pulse width is 200 milliseconds, and the allowable voltage droop is 5 volts. Plugging these parameters into our equation, we find that we need a 40,000 microfarad capacitor. Since our operating voltage is 28 volts, we'll apply a D rate and specify a 50 volt capacitor. This slide outlines possible solutions for our 40,000 microfarad 50 volt capacitor requirement. As we evaluate these options, we must ask ourselves the questions you see on the right. How important is the size and weight of our capacitor solution? How will the ESR impact the capacitor's performance? What are our shelf life needs? This slide summarizes the data from the previous slide with cost estimates included. If your application is not sensitive to size, weight, or hermeticity, and can accommodate the top aluminum electrolytic option, you should absolutely pursue that route. However, if these are critical parameters, in addition to reliability, shelf life, and all the other items we had previously discussed, then you really must consider other options. In this next case study, we consider a radar application where the current is 20 amps, the pulse width is 200 microseconds, and the allowable voltage droop is 1 volt. Now, using our same formula to calculate the capacitance needed, we determined that we needed 8,000 microfarad capacitor. Applying our D rate to our 60-volt operating voltage, we specify a 100-volt rated capacitor. With advantages in gallium nitride or GaN technology, we have seen an increase in voltage requirements for these applications, so 60 volts is not uncommon nowadays. Next, we see our options to meeting our 100-volt, 8,000 microfarad requirement. Again, we ask the same questions as seen on the right. If this is a ground-based radar system, perhaps minimizing space and weight may not be as important, but in an airborne system, this is a standard requirement. Additionally, a capacitor with a higher ESR can generate more heat, which may require the addition of a complex cooling system. Again, on this slide, we see a summary of our options. Aside from the obvious design considerations as we have discussed, we actually see that some of these solutions require multiple capacitors that will impact assembly costs and affect overall system reliability. In addition, a capacitor's small size and weight will allow a designer to put energy storage closer to the emitter, reducing the need for additional wiring. Nonetheless, asking ourselves the right questions as we compare our options help ensure we've chosen the best capacitor for our application. Now, let's talk about the importance of ESR. As previously mentioned, the capacitor's ESR, the equivalent series resistance, is a critical component to take into consideration, particularly in high current applications. ESR contributes to the voltage droop, which has a direct impact on how much capacitance is needed. As a result, the formula we've been using really must be amended to take ESR into consideration, as it contributes to the voltage droop. As you see, we've added the voltage droop attributable to the capacitor's ESR to the denominator of our equation. The higher the cap ESR, the greater the voltage droop, and the more capacitance you need to overcome that voltage droop. Now I'd like to talk a little bit about how Evans caps work. The Evans hybrid capacitor is a capacitor that pairs a tantalum electrolytic anode in series with a ruthenium oxide pseudocapacitive cathode. The anode stores its charge by the creation of an electrostatic field, with the tantalum pentoxide being the dielectric. The ruthenium oxide cathode uses an electrochemical redox reaction to store the charge, which has capacitive behavior, hence the term pseudocapacitance. This pseudocapacitance allows for much higher energy densities versus traditional capacitor technologies. This technology allows Evans tantalum hybrid capacitors to have higher energy densities combined with higher power densities compared to traditional wet tantalum technology. Evans caps offer superior electrical performance, particularly in regards to ESR, energy density, and power density. They also provide high reliability, significant swap savings compared to traditional capacitor technologies like tantalum and aluminum electrolytic, and can withstand high vibration and shock environments, which make them particularly popular in downhole oil and gas exploration applications. The rugged construction of the capacitor provides superior resistance to the environmental conditions against corrosion. For example, you can even throw our capacitor to the bottom of the ocean, come back 100 years from now, and it will pretty much look the same and be able to operate as if it was built yesterday. Thank you so much for your time today. I'm going to pass this back to Stefan, and I will be available to answer any questions you may have.
Thank you very much, Misha. It is now time for our Q&A session. If you'd like to submit your questions, you can do so through the Q&A widget on the top right-hand side. But it looks like we have some questions coming in already. Our first question for today is, what is the current limit of Evans cap?
Great question. We actually don't have a current limit. Our current limit is actually truly only we're only limited by our internal resistance, really our ESR, which is extremely low. So our current is just limited by your ability to pull heat out of the capacitor to ensure it operates at its rated temperature and last for its rated lifetime, of course.
Thank you very much for that answer. And moving on to our next question for today. What are typical D-rate rules for Evans caps?
Oh, of course. So Evans caps Evans caps are rated for 2,000 hours for life at rated temperature and rated voltage. For every 10 degrees below rated temperature you're operating, you get an approximate doubling of life. Additionally, for every 10% below rated voltage you operate, you get another approximate doubling of life. So these are the general rules of thumbs that are typically used as our capacitors are designed into their application. So as I mentioned, the baseline is 2,000 hours of life at rated temperature, which is 85 degrees C for the vast majority of our capacitors, and then whatever the specific voltage rating are as well there too. For military applications, people typically apply a 60% voltage D rate.
Thank you very much for that answer. And before we move on with the next question, just a quick reminder to the audience, you can still submit your questions through the Q&A widget on the top right-hand side. But moving on to the next one. What properties make Evans caps space grade?
Oh, of course. Well, NASA has a standard for capacitors. It's the NASA INST 002. There's 3 different levels, level 1, level 2, and level 3. Our customers typically ask us to approve our capacitors to level 2. The capacitor essentially must withstand a series of tests and successfully, of course, pass them with sometimes few failures, maybe 1 of 6 failures, and sometimes 0 failures allowed. Typical testing requirements are thermal shock. You put the capacitor in a chamber and you cycle the temperature from perhaps plus 85 all the way down to minus 50, and you go back and forth doing this thermal shock. And the capacitance at the end of however many cycles are specified, 10, sometimes 50, the capacitor still needs to function at the end of that. There's specific hermeticity tests to ensure the capacitor is successfully hermetically sealed. There's voltage surge testing and a whole battery of tests. So I would certainly encourage I would encourage you to look at the NASA INST 002 standard to see the battery of tests that capacitors must pass in order to be qualified for space flight.
Thank you very much for that answer. And I believe we are approaching the end of today's webinar, unfortunately. So that just leaves me to thank Misha for the great presentation and to Evans Capacitator Company for sponsoring this session. If you didn't get your questions answered today, please keep in mind they can be answered at a later date offline. To the attendees, you receive an email shortly with instructions on how to access the on-demand version of the webinar, or you can do this from the website, which is www.business-review-webinars.com. We look forward to sharing more webinars with you, so please keep an eye out on the website just mentioned and follow us on Twitter @BRWebinars for daily updates. Thank you once again, and have a great rest of your day.
Thank you, everybody.